All right, so now let's move on to power functions. So I'm just going to zip through these. The points I want to make here are just, these are some functions that we should be aware of, and we should know basic graphs of these functions. So the power functions. Power functions are functions of the form x to the a, where a is some fixed real number. So when in the case where that a is some even integer, like x squared, that's that red curve here, we get a parabola. When we have x to the fourth, we get this sort of steeper thing that becomes a lot flatter as it passes through the origin and then becomes steep again. And you can see that the higher the power is on the x, the more steep this function is out here. But once we get inside of, you can see here this is 1 and that's -1. Once we get inside this interval from -1 to 1, the higher the power is, the flatter the function's graph becomes. Notice they all pass through this point here and this point here, and that's because 1 raised to any power is 1, and -1 raised to any even integer power is 1 as well. So they all pass through this point, but the higher the power is, the bigger the function is beyond 1 and less than -1. But the higher the power is, the smaller the function is in the interval from -1 to 1. So notice that all these functions have symmetry. They have what we call even symmetry. And what is even symmetry? It means they are symmetric about the y-axis. The y-axis looks like a mirror line. Whatever happens over here, it's just being mirrored over here. An algebraic way to write this symmetry down is that if I plug in -x, I get the same value coming out of the function as if I were to plug in x, right? F of 1 is the same as f of -1. Okay, what about if I change the power? Instead of an even integer, I make it an odd integer. Well, then our functions look like this. Again, we've got our power of 1, which is our linear function, and then the higher the power goes, the bigger the function is out here beyond 1 and less than -1. But in the interval -1 to 1, the higher the power is, the smaller the function gets. So the flatter it becomes at the origin. These function values are all negative down here because when I take a negative number to an odd power, the negative sign survives. And so these functions are positive when x is positive and negative when x is negative. They have what is known as odd symmetry. What does odd symmetry mean? It means that they are symmetric about the origin. So in even symmetry, there was a mirror line. They were symmetric about the y-axis. In odd symmetry, there's a symmetry about the origin. So there's this rotation that happens, 180-degree rotation around the origin, and whatever happens over here, 180-degree rotation, rotates it onto exactly what's going to happen down here. The algebraic way to write this is that f of -x, maybe I don't want that to be confused with a negative sign, so I'm going to use a bullet point here and a bullet point there. F of -x is equal to negative f of x, right? F of -1 is the same thing as f of 1 with a negative sign in front of it. And so again, just observe that all these functions have 1 point or 2 points in common. At the value 1, they all take the function value of 1, and at the value -1, they all have the function value -1. Okay, what about instead of having these integer powers, we take rational numbers as powers? So the basic examples are, what about x to the 1/2? Well, that's the square root function, and that's drawn in red here. And then as the power gets smaller, so 1/4 or 1/10, then the function values get smaller beyond 1. But in between 0 and 1, the lower the power is, the larger the function values get as compared to one another. And they all pass through this point, 1, 1. So these are our root functions, and just observe the behavior. Notice that the function's not defined over here for negative inputs because you can't take the square root of a negative number, you can't take the fourth root of a negative number, you cannot take the even root of a negative number. If we look at the odd roots now, like the third root, or x to the 1/3, or the fifth root, that is x to the 1/5, then we get the same sort of picture that we had before with the even roots, except now they are defined over here. So they all have the root of 1 is always 1, but now for negative values, we can take the cubed root and the fifth root and the 11th root. We can take odd roots of negative values and we get negative values out. So they've got this odd symmetry. That means we can rotate everything that's going on in quadrant 1 and get what's going on in quadrant 3. And then I'll pass this point as well. So again, I'm just going through some of these basic functions that we've seen lots of times before and just refreshing ourselves with what their graphs look like. Now, what about a polynomial? So we've got a function defined by integer powers of x, so x to the n minus 1, and some coefficients in front of it. So here's some examples, like this one down here, x cubed minus 2x squared minus x plus 2, or another example. This highest power of x that occurs, in the first one it's 3, in the second one it's 4, that's known as the degree of the polynomial. All our coefficients in this general form up here, all these a's, they're real numbers. And again, let me just reiterate, all the powers, the n and downwards, are integers. So you may remember that when you've been dealing with polynomials, you often deal with them in one of two forms, either the expanded form or this form here, which is known as the factored form. Now the point with the expanded and factored form are each one of them gives us different information about the function. So let's just indicate what kind of information we get. So what do we get from the expanded form? Well, things we can get right from the expanded form are we can find or see the degree. Immediately we can see the degree of the polynomial. What's nice about being able to see the degree right away is that we get the end behavior immediately. What do I mean by end behavior? Well, I mean this. So look at this first polynomial here, x cubed minus 2x squared, etc. What's the end behavior? The end behavior is what's happening when x is really, really, really big. What's happening as x gets huge? Well, as x gets huge, x cubed is going to dominate all these other terms. These don't matter much when x is huge. So what that means is the overall shape of our function when x is huge, what's going on at the ends, is really roughly the same thing that goes on with just the cubic function near the ends. And what does the cubic function do near the ends? Well, as you head off towards positive infinity, it blows up. But as you head towards negative infinity, it goes down. And so we see that immediately, that that's how this function's got to behave. So the end behavior, what I've drawn here by these little dotted circles, that's determined from the degree of the polynomial. So that's determined from this expanded form. What else do we get? Well, we get the y-intercept immediately. Just plug in x equals 0, and we see immediately that the constant term hanging on the end is where it's going to intersect the y-axis. In particular, what we get is we get global information about the graph. You know, all of the stuff that I've just indicated here is sort of what's going on big picture. What's the end behavior? How many bumps are there? Well, if the degree is 3, we can have at most 2 bumps. And we see that here. The number of bumps is going to be at most 1 less than the degree of the polynomial. So all this stuff here is what we know as macroscopic properties, big picture properties. Okay, so what about the factored form? What kind of information does it give us? Well, the factored form. Well, we can immediately see the roots. Where are the, let's maybe indicate this by roots, I mean the x-intercepts. Where is the function 0? For what inputs does the function vanish? We also get the behavior near the roots. What do I mean by the behavior near the roots, or behavior at the roots? Well, let's look at these two examples here. The roots are going to be, we can see them from here, it's where this is going to be 0. So that has a root at -1, at 1, and at 2. So we can see that here, -1, 1, and 2. How does the function cross the axes there? Well, the root -1 corresponds to this factor here. It's raised to the power of 1, so there's only one factor of the form x plus 1. So that indicates that when it crosses the axes at -1, it should cross it like the line. And similarly at 1, it should cross it like a line. So this should be crossing it like a line here, crossing it like a line here. And you may say, well, I don't know really what that means. Okay, so we'll compare it with this other one. When we look at the other one, we see, oh, it's got a root at 1, so it's a root right there. And it should cross it like, you see a power 2 here, so it should touch at that root like a parabola would behave, like a quadratic would behave. And so it would turn around there. And it would turn around and look locally like a parabola at that point. Whereas at 2 and -1, it should cross like a line crosses. So that's what I mean by behavior at roots. Maybe I should say how it crosses or not. In the case of, we're essentially not crossing here when it looks like a parabola, but how it crosses or not. So these are, in some sense, microscopic properties. So maybe I should indicate that by contrast, macroscopic versus microscopic, or global information. Here we get local information, what's going on at and around the roots. It might be good just to come up with a more general visualization. So let's plot that last example here. So I've plotted it. What I'm going to do is I'm going to just introduce a slider. And what I'm going to do with this slider is I'm going to change my exponent. Instead of being 2, I'm going to change that exponent to be n. So we'll go n. Now nothing's changed because my n value is still 2. Now I'm going to get it to show it as a slider. And in order for things to behave nicely, I want to make the values that this slider goes over the integer values, let's say starting at 1 and going off to 5. That's fine. Okay. So now what happens? Now, as I play with this slider, watch this point right here. Because notice that this point right here, that corresponds to this factor of the polynomial, x minus 1 squared. So I'm saying that this power here should tell me how it's crossing there. So right now it's behaving like a quadratic. If I back it up to 1, now it should cross like a linear function. And it does. If you zoom in far enough, it looks like it's crossing like a line would cross there. Okay. What happens if I go to 3? Well, now look at it. Now we see that it crosses there, but it doesn't cross like a line anymore. If I zoom in close enough, it kind of resembles how a cubic would cross. A cubic crosses the axes by coming down, going horizontal temporarily, and then continuing on past. So it looks like it would cross like a cubic crosses. And similarly, if I go up to degree 4, it doesn't cross anymore, but it behaves like a degree 4 polynomial where it becomes really flat there, becomes really flat. And then if I continue on, now it crosses like a degree 5 would, becomes really flat, but still crosses, but becomes really flat. So that's what I mean by the factored form. We can see the roots, but the powers on those factors would tell us sort of the behavior of how those roots look. How is the function crossing or turning around at those points? So again, just an illustration as We have expanded and factored form of the polynomials. Both of them are useful. It depends what kind of information you want. Now our next class of functions that I want to look at are the rational functions. So these are functions which are formed as the ratio of two polynomials. So here's some examples. Constant polynomial 1 over polynomial x, or 1 over x squared, x plus 1 over x squared minus 4, and so on. So the thing to notice here is that the first two examples are ones that we should be really familiar with. What's the general shape of 1 over x? Well, it's not defined at 0. What's happening near 0? Well, I think about as x gets closer and closer to 0 through positive values, then 1 over a number that's positive is positive, but 1 over a number that's positive and close to 0 should be a really big number. So we see that these things are heading up, blowing up to infinity here. But as I head off in this direction, x values get bigger and bigger and bigger. 1 over a big positive number should be a small positive number, getting close to 0. So we see that we've got this horizontal asymptote here. So we can start to see immediately the vertical and horizontal asymptotes just by imagining what happens as x goes to 0 or x gets big. And similarly, 1 over x, if x is negative, they would be negative value. So it looks like that. What happens if I square the bottom? Well, now all the function values are positive. We still get that sort of behavior where as x gets small, close to 0, then the reciprocal of it's going to get big, so it's going to blow up, have a vertical asymptote there. But as x gets big in either the positive or negative, so the magnitude of x is getting big, 1 over a big number is a small number, so we've got these horizontal asymptotes, this horizontal asymptote of y equals 0. So the function gets close to 0 as we head off in either of the two directions. What about the next one? Well, we got x plus 1, x squared minus 4. So what kinds of information we can get from this? Well, the idea is that if we look at the factored form of this, x plus 1, x minus 2, x plus 2, the numerator, since there's no common factors, the numerator is going to tell us the zeros, where it's going to cross the axis. So it should cross at -1. We see it does. The denominator is telling us there will be vertical asymptotes at 2 and -2, and we see those here. We could get a little bit more information if we wanted to. We could say, well, what's happening, let's say, near 2? If I'm just to the left of 2, so value is slightly smaller than 2, what's my function doing? How do I know it doesn't blow up this way, go up, rather than going down? Well, if I'm slightly less than 2, then x plus 1, that's just a number that's slightly less than 3, so it's positive. If x is slightly less than 2, then this is a negative number. But x plus 2, that would be a positive. So I'd have positive divided by negative times positive. So the whole thing is negative. And we see that this piece is going to 0. So I got a negative number that's blowing up. And so it would be coming down in this direction. So you can do this quick analysis just to see what is the sign. I know there's an asymptote there. What is the sign as I head towards it from the left? What is the sign as I head towards it from the right? Now I'm starting to get you to think in this direction with examples that we are already familiar with, because these are the kinds of things we're going to formalize in calculus. We're going to talk about how we approach a number from the left or from the right, and what happens to the corresponding function values. This is starting to touch on limits, which we'll deal with a little bit more formally. And for this last example, again, we factor it. We've got that the denominator factors x plus 2, x minus 2. Oh, these can cancel off. And this is really just the function 1 over x minus 2. But I can't cancel it without changing what looks to be the domain. So I'll roll this up a bit. So for x not equal to -2. Because our original function wasn't defined at -2. The top and the bottom would both vanish there. It wouldn't make sense to plug it in. So I can reduce it. I can write it in this way, just as long as I make sure I tell you for x not equal to -2. Now it looks like the function 1 over x minus 2, which is essentially this one here, shifted to the right 2 units. And we'll talk about shifting and transformations in the next section, but just maybe a quick reminder that this thing is this first one shifted to the right 2 units. But there's also one more thing that's not really apparent in the graph about what's going on with it. What is going on? Well, it's not allowed to be defined at -2. So there's a hole there. So I don't know if you can see that. but I've indicated that there's a hole in the graph there. It's not allowed to be defined at -2 because -2 doesn't make sense to plug in there. So the idea with the rational functions is we can spot asymptotes and we can spot zeros where it crosses the axes. We can also spot holes. Those are where there's going to be a common factor of top and bottom. So what you would do is you take your rational function like we've done in this last example. We'd factor the bottom and the top. We'd cancel any factors, indicate that those are the holes. And then any zeros of the top are going to be where it crosses the x-axis. And any zeros of the bottom, any values which make the bottom 0, are going to be where our asymptotes are.